Hi, everyone. Let's pick up where we left off, talking about 2-3 trees. We sort of went over just the general structure of a 2-3 tree in the previous video. We talked about it really abstractly using just like variable D0, D1, D2 for the data points and talked about, how the 2-3 search tree would be organized. Let's look at some actual numbers here. So here we have a 2-3 search tree of height 2. And before we do anything with it, let's just make sure that we understand both why this is a valid tree and approximately what the data might look like if it was being stored somewhere. Let's start with how the data would be stored. And let's just look at this much of the tree just for a moment to make our life a little bit simpler. Hold on, there we go. Just that much of the tree for a second. Because sometimes I find it's a little bit confusing the way that these are drawn. So what we know is that each of these circles or ellipses represent a node. And in memory, we're going to just show how this would be drawn. Pretend that this is memory. There we go. That's my beautiful memory diagram. So our root, actually root would be on the stack. So the root variable is a reference to the node that lives right here. In this node, we have our data array with two primitive values in it, 11, oh, it's so tiny, 11 and 22. Then you'll see we have our children array with 3 pointers. So let's do that as well. Children. Now you might put more things in your class, in your more instance variables. Why is this not auto squaring? There we go. You might put more things in, like keeping track of the number of children that you have, like an actual variable for it, or the number of data points. But these are the main pieces of information that we know we have thanks to this picture. So this is pointing at one node, this is going to point at a different node, and this is going to point at the third node. We'll see that children at spot 0 is pointing to a node. Right there. And this node also has 2 data points, 2 and 8. And it also has a children array. And we can see we have 3 children. So this first one would be pointing there, this one would be pointing there, and this one would be pointing there. But as I said previously, I'm not actually going to draw out all the way down this far because it gets really messy. I don't have that much space here. But we know that each of these is referencing a child somewhere. Those are also references to nodes. Next, we can look at 18. Here's our node for 18. There we go. It also has a data array. In this data array, we have an 18 here. And then we have nothing. That's such a messy 18. Let's see if I can do better. That's medium. And then there's nothing in the other spot because we only have 1 data point in here. And then we also have that children array. Oh, for some reason that drew an arrow and not a square or a rectangle. And here you can see that we have 2 children, not 3 children. And what's mostly standard is that this one would reference a child, this one would reference a child, and this one is null. So even though it gets drawn like left and right, technically we'd put them in left and middle, and like one more would be empty over here rather than leaving gaps in our child array. So I feel like that makes sense because we don't like to leave gaps in things. This point's here, this point's here, but the way it's drawn and the way it's stored do look a little bit different from each other. And then this last one over here, which I will do just to finish off the point we're making here, is the same. We have a data array here with a 26 and nothing else, which means that we'll have our children array where we have 2 pieces of data and 1 null. So each of these are referencing data somewhere else. If we relate it back to our original picture, we can see that we can see that children at 0 here is pointing right there, and we can see that children at 1 is going to be pointing right there at those nodes. So that's our like memory diagram representation of what's actually happening here. But of course, when we draw it out, we just put our numbers in the node, and then these are the references coming off of it. Okay. The last thing that I said I was going to do as part of this was also to make sure that we understood why this was a valid 2-3 tree. We can see that each of these have 0 children. So they're all leaf nodes and they're all on the same level. So the height of our tree is maintained all the way across every single path from root to leaf. We can also see that D0 is greater than or is less than D1 in all scenarios where there are multiple keys within a single node. So we're maintaining that search property. We can also see that all children, all like internal nodes and our root have either 2 or 3 children. So that maintains that as well. And then we can see that this is strictly less than the left value. These are between the 2 parent values, and this is greater than the right parent value. And that holds true in all cases across the board here. Both of these are greater than 18, less than 26. Both of these are greater than 26. And then that holds true at the next layer as well. So both of these are less than 11, which means that all of this is going to be less than 11. This is between 11 and 22, which means all of these are between 11 and 22. And this is going to be greater than 22, which means everything on this side is greater than 22. So we can see how the 2-3 search tree structure is maintained. So we're going to start by talking about searches, and all of our algorithms start with our root node. So each node has a pointer to each of its child nodes. And of course, our tree, just like our linked lists, have a top or root pointer. So let's start with our search. Let's imagine for a second that we're going to try to find 19. Our search is actually really straightforward. We can determine how many keys we need to look at. We can try to find our search value. If it's not one of these values, we just determine which path we need to go down. And we keep going until we either find the value or we hit the end. So for value 19, step 1 is it equal to this? No. Is it greater than or less than? It's greater than. Is it equal to this? No. Is it greater than or less than? It's less than. We come straight down here. Is it equal to this? No. Is it greater than or less than? It's greater than, and there's no other value here. So we go straight down here. We come here. Is it greater than or less than? Or sorry, is it this value? It is, and we stop. If instead we were looking for, let's say, 17, we would do the same thing where we'd start looking for the value 17. Right here, we'd recognize it falls right between. We'd come here, see it's not the same, but that it goes to the left. We'd come here and see that it is greater than the rightmost value. And we would be like, oh no, we fell off. There's nothing else to do, so it must not be in here. So it's very, very similar to our binary search tree, just with looping through children instead of just assuming there's only either a left or a right child. Right? Here it is sort of the stepwise algorithm going through it with the highlighting of the nodes as we've seen before. So now let's just imagine for a second, let's take a step back and make it more abstract. Let's assume we're searching for a 2-3 tree node K. So we're looking for some node K through our 2-3 search tree. If there's only one value in the node, we can check to see if it's the value. If not, go down one path, otherwise go down the other, right? If it's less than, go down child 0. If it's greater than, go down child 1. Easy peasy. So I'm actually going to write that though. I'm going to say if K equals value, then we're done. Else, if we're not at a leaf node, we can go and check more things. If K is less than the value that's there, go down child at spot 0. Else, go down child at spot 1. Okay, if the node contains 2 or more values, we have a little bit of extra checks that we have to do here. We still want to make sure that we can still do that first check to see if K is equal to D0. And if it is, we're done. If K is equal to D1, we're also done. So if we find it in one of those places, then we're done. But if we're not at a leaf, we can just check if K is less than D0. We're going to go down the child 0 path. If K is greater than D1, we're going to go down the child 2 path. If it's between the two values, so else, we go down the child 1 path. We go right down the middle. So it's kind of an easier way to check it. You could check it like in order, check if it's less than D0, else if it's less than D1, else it must be greater than D1. There are options. And again, we figured out how our search ends. Our search will end if K is equal to the value that we are looking at. So whether that's the single D0 value or D0 or D1, or if K does not equal any of those values and we are at a leaf, meaning no more traversals. So we've either found it or we don't. The code itself is not too bad at all. We do know that this is pretty straightforward, and we'll talk about the analysis later, actually. I was going to talk about it now, but we'll just leave it for a minute. No analysis right now. Now, the search is reasonably straightforward, but it's hard for us to test a working search method without having an insert. And unfortunately, there are a lot of properties that we need to preserve when we're trying to add a new node into our 2-3 search tree. If we start from nothing, it's really easy. That's our easiest base case, where if our root is null, then we can just make a brand new root node with our data point, and it will essentially make our brand new object where data is an array. We'd end up storing one piece there, and our child array would be null everywhere. Now, I will say that when it comes to doing inserts, it's often a good idea to sort of leave yourself a little extra piece of memory space on each of these, because then if we magically fill all these up, we are too full. And we're going to see what we do when that happens in just a moment. So I've been drawing these thus far as being arrays of exactly size 2 and 3, but in actual implementation practice, I recommend your data array being of size 3 and your child array being of size 4. And we will see why in just a moment. Okay, so now if we're going to go and insert the value 2, so first we inserted 1. If we're going to go and store the value 2 now, we'd come in, we'd see that we still have space inside of our data right here. And we'd either move data 0 over if we want to maintain that order, or we would just insert our new data value directly into here. So we don't actually have to make a new node when we insert 2, we just update the data array of our root. If instead we inserted 2 first, and then we inserted 1, we would have to push 2 over and insert 1 into D0. So here 2 is D0, here we have to push it over. So there is some logic that has to be done there as part of that insert to make sure that we're maintaining the order within our data. All right, so now we're going to talk about what happens to actually insert too many values into a node. So this is why I said that, like, if we move from this position right here, this is in D0, this is in D1. If we really wanted to do this in an intelligent way, our data array could hold up to 3 pieces of value, 3 pieces of data. And when we insert something into 2, we are too full. So we can keep track of that a little bit easier if we leave space for that extra piece here. And we'll see why that's going to help us again in just a moment. So in order to do something with this, when we realize, oh no, we've added too much data and we're overflowing as a node, we're basically going to follow our search algorithm until we reach a leaf, add our new value to the leaf, and then we will split our nodes to move our way through. So here this says, like, don't create a new leaf yet, right? So if we allowed our data object here to only hold 2 pieces of data, so it's an array with 2 pieces of data, when it comes time to enter in that value of 4, you'd be forced to do it like this, right? If we don't make space in our data array for a 3rd piece of data. But notice that there is a comment here that says, don't create a new leaf node yet. So the best and easiest way, actually maybe not best, but certainly easiest way to ensure that we adhere to that rule that says don't create a leaf node yet is to literally do our insert into this node and let it be too full. So we do that and we realize it's too full. If the right here, our resulting node has 3 values, we're too full, we're going to call a brand new method called split. And split is pretty straightforward. All we do with a split is push up the middle value and separate the children. So originally we had D0, D1, D2. We're going to push up the middle value, and this will transform to the middle value being pushed up, D0 and D2. So this one will be transformed into a new root node that is just 2, and the children are like this. So when we actually do this splitting action, we should note how it's being done a bit more algorithmically to split our leaf node. So again, notice that we're saying split a leaf node, which means it's different if we want to split an internal node. But to split a leaf node, we move our middle value up 1 row to its parent and break up the left and right values into separate nodes. In this case, since we have no parent node, we have a new root. It's entirely possible that we may not always need to make a new root. It depends on if there's space in our parent or if we have to recursively continue to split parent nodes all the way bubbling back up to the root. So in general, we do our search to find a leaf, we do our insert here, and then we bubble back up with our splits. This is inherently different from what we did with binary search trees. In binary search trees, as soon as you made that root node, it never changed. Everything else had to be entered relative to that root node. This is completely different. In this scenario, our root node is changing all of the time. We start with our root node being whatever it is, but it's entirely possible that we'd enter enough values that our root node gets pushed up and we have a new one. And this can keep happening. So rather than our tree growing at the bottom, we're entering values at the bottom, but we're constantly growing from the top. So it's very, very different than what we were doing in a binary search tree. Okay, so here is that result after our split, as we said, and thankfully looking at it like this, we can feel reasonably confident on how we had to do this split. But it does get a little bit more complicated, both visually and implementation wise. So let's just keep going for a minute. We can see here that we inserted 11. How did we do that? Well, here's 11. And we walked here. We said, are we going to the left or the right? We're going to go to the right. Are we a leaf node? No. So we walk along. Here we said, are we going to go left or right of 4? We're going to go to the right. Are we a leaf node? Yeah, we are. So let's just stop and let's just add 11 right here. Are there too many keys here? No, we're done. Those are the questions we ask ourselves as we go. It's a good idea to write out those questions if you're still trying to figure out how these things are working. Let me just cover up that 13 for just a second. Okay, so then we're going to go and insert 13. We start right here and we say, are you a leaf node? No. Are we going to the left or right of our data point here, or middle? In this case, since there's only one piece of data, we are only deciding between going one way or the other. We are bigger than this piece of data, so we walk this way. Are we a leaf node? Yes, we are. So let's figure out where we need to sit inside of our leaf node. We realize we need to sit right here at the very end. Then we ask ourselves, are we too full? And in this case, the answer was yes. So what happens in this case, just get rid of that. What happens in this case is the same as before, only now we have a parent node. So we punch the middle value up and we split the children up. So what that actually will look like is we punch that middle value up and we split our children into 2. And there we go. Okay, so we can already see that our height of this tree is inherently better than if we were doing a binary search tree. If, let's just imagine for a second, we instead did this in a binary search tree pattern. First, we would insert 1, then we'd insert 2, then we'd insert 4, then we'd insert 11, and we'd insert 13. We'd have a height of 1, 2, 3, 4, and here, so our binary search tree here has a height of 4, and our 2-3 tree height over here is only 1. So it's substantially better, clearly. Okay. So we split and we moved up. Anytime we do a split and a push up like this, we have to ask ourselves, is the parent too full? So anytime we do this kind of a move where we have to do a split and punch, we ask ourselves, is the parent too full? If no, we stop. If yes, we have more work to do. We actually asked that question here as well. It just looked a little bit different in this case here. So we punched the parent up. Since there was no parent, it became a new parent. And we still had to ask ourselves, is this parent full? Now, since we created a new parent, we already knew it wasn't full, but we could, in theory, sort of like, what's the word? Implicitly? No. We could sort of like ask the question anyway of, is the parent full, even though we know 100% it's not, just to sort of understand how it would algorithmically make sense. Okay, cool. So we ended up with, as we said, this beautiful diagram here. Let's continue. And you can see here, we're going to add 18 and 19. So let's just see what happens before we go down there to look at it happening. First, we try to add 18. We come here, we say, are you a leaf node? It's not a leaf node. And we see that we have 2 values. So we have to determine if we need to go to the left, to the middle, or to the right. We realize we're going to go to the right. We walk down the right. We say, are you a leaf node? The answer is yes. So then we just determine where we need to put our value. We see we want to put it right there. And so we do. So let me just nicely draw this. Like this would end up becoming 13 and 18. Then we want to enter 19. So what happens here is we once again start up at the root node and we say, are you a leaf? The answer is no. We figure out which pathway we need to walk down and we do so. We come here and we ask, are we a leaf node? And the answer is yes. So we just determine where we're going to put the value. We realize we want to put it right here. Let's go ahead and do that. 19. And then we ask ourselves, are we too full? And the answer is yes. Since we are too full, we're going to do a punch and a split. What that would result in is a tree that looks something like this. 2, 11, we punch up that 18. If we're punching up the middle value from this side of the tree, it ends up right at the end. If we're punching up a middle value from here, it would end up in the middle. And if we're punching up a middle value from the leftmost child, it would end up as the new leftmost value. Once we've done this punch up, this didn't change, but we still had to split 13 and 19, so those got split like this. We can now see why I had originally said you might want to make your implementation of your data points have enough room for 3 values, and our implementation of our children have enough room for 4 values. Because as I said previously, after we do this punch up, we need to ask ourselves, is the parent too full? And as we can see, this is yes, the parent is too full. So we have to do this again. We punch up our middle value and we split. So what will that look like? It's just, whoop. Let's just pick this up. I don't want to pick up the white. There we go. So we split it like this. We asked ourselves, too full? The answer was yes. So we had to do another punch and split. 11 got punched up. We split these 2, and the children just split in half. And like magic, we have a new binary search, or a new 2-3 tree. We would once again ask ourselves, parent, too full? And since the answer is no, there are no changes to this tree. So we're inserting to the leaf, and then if we're too full, we punch up and check again. If we're too full, we punch up and check again, and we keep doing that until we can say, no, we are not too full. So here we just added 18 like we did originally, then we added 19. We're going to do that punch and split as we did previously. We can see it right here, punched it up, split these into two, and then we once again asked ourselves, are we too full? We can see that where we punched our value is indeed too full. So what are we going to do now? We're going to do our punch and split. We punch the middle and we split the children, and everything just splits right down the middle. And there we go, exactly where we ended before. Okay. So here's an exercise where I would strongly recommend you pause this video and you try it yourself before we walk through it together. We would add values 22, 25, 26, and 27 to our 2-3 tree in this order and see what happens. So pause the video, try it yourself, and then come back as I continue to show this example. Now the answer is shown below in many slides, but I'm going to go ahead and walk through it here with a full explanation. So the first thing we try to enter is our value 22. We come here, are we at a leaf node? Nope. We only have two values, so we try to go both. We determine which side we need to go down. We go down it. Are you a leaf node? No. Determine which way to walk. Are you a leaf node? Yes. Determine where to put our value. We realize where we need to put it. Just gonna do what I was doing before. And then we ask ourselves, are we too full? And the answer is no, we are not too full, so we're done. Next, we're gonna go ahead and enter 25. This goes the same way. Are you a leaf node? No, we determine the path to take. Are you a leaf node? No. Determine the path to take. Are you a leaf node? Yes. Let's go ahead and enter this into the leaf node. And then we ask ourselves, are you too full? And the answer in this case is yes. So we need to do a punch and split. So when we do a punch and split here, we once again will punch up our middle value here. 18 and 22. And we can do our split of 19 and 25. 19 and 25. Okay, next is adding the value 26. Let's go ahead, grab 26. Are you a leaf node? No. Walk down the correct path. Are you a leaf node? No. Walk down the correct path. Are you a leaf node? Yes. Add it right here. 26. Is it too full? No. Then our tree is done for right now. Let's go ahead and add 27. Are you a leaf node? Nope. Walk down here. Are you a leaf node? Nope. Walk down here. Are you a leaf node? Yes. Let's add it in. Then we ask ourselves, are you too full? And the answer once again is yes. So we will punch up the middle value. Since we're punching up the middle value on the right side of this, it will become the new right value for our parent. So 26 gets punched up to here, and 25 and 27 get split here. 25 and 27. Since we did a punch up, we have to ask ourselves, is this too full? You'll notice that the answer is yes, it is too full. So we do the same thing again. We're punching up to the same side of our node we're going up to. So this middle value will come right up into here. Meaning, let me just put this right here. Let me do just another color since we're doing this punch up becomes, oops, not 2, sorry, 11 and 22, because we punched this value up. And then we separate the other two values, and we separate our children right down the middle, right? 50-50 divorce split. So we end up with the new middle value here being the other one's child with its two children, 13 and 19. And then this side will be 26 with its two children being 25 and 27. Let's just go ahead and cover up whatever we need to cover up. What did we say? 25 and 27. Put this here. Hold on. This can just go there. Try to make it somewhat nice. 25 and 27. And there we go. So now we still have our height minus 1, our height minus 2. So we have a height of 2 in this tree. This is going to be 2, this is 1, and this is 0, which makes sense because everything off of this top node has 2 edges from root to leaf. Everything off of this subtree or this subtree or this subtree has a height of 1. And then everything off of this subtree, this subtree, this subtree, this subtree, this subtree, and this subtree all have no edges, so it is a height of 0. And you can walk through that again with the pictures here. You don't get the cute little walking down the pathways that I do in my animations, but we can still find our final answer appropriately right here at the end of this. Okay, so we can ask those questions as we go. Are you a leaf? If yes, enter and then see if we need to split. If you're not a leaf, go which way we need to go. And by sort of asking ourselves those questions, we can start to understand how we would build out this insert algorithm. So as we can see, the tree grows only from the top. When a new root node is created, all the branches in the tree get longer by 1. And this is how the height balance is preserved. In our example before, we had our values being added in ascending order. And because we were adding them in ascending order, right, we literally added, let me just do it here. We first added 1, then we added 2, then we added 4, then we added 11, then we added 18. Nope, just kidding. Then we added the value 13. Then we added the value 18. Then we added the value 19. Then we added the value 22. Then we added the value 25. We added the value 26. And then we added the value 27. Had we done this in a binary search tree instead of a balanced 2-3 tree, we would have ended up with a height of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because we would have had just this linear connection of them all down the right, like the right subtree. But in this beautiful scenario, instead, we end up with a height of 2 and a very nicely balanced tree, which is obviously great news. We can also sort of see, given that I just showed that, what a in order traversal might look like of a 2-3 tree, although we will cover that going forward in future videos. Okay, so like we said, the implementation of a 2-3 tree will have a private inner node class. What fields should this node contain? Take a second to think about it. Ideas I've already given you is whatever your data points are, I strongly recommend it being an array with 3 spots, and that you have children with 4 spots. I would also recommend keeping track of how many pieces of data you have, because that alone is enough information to know what's going on. For example, if you have things that we can glean from just having this data, we can determine if we're a leaf, because we can figure out how many children do we have. If we have no children, then we're a leaf. And as long as we're filling our children nodes from left to right, we really just need to see if we have a left child. If we don't have a left child, if it's null, that is a confusing way of writing it. If it's null, we are a leaf, because we won't have a child at any other position if there's no child at spot 0. What else can we glean? If I know that my num data is 1, then I probably have, I'm either a leaf, hold on, I'm either a leaf, is leaf, or I have both a children at spot 0 and a children at spot 1. And we know that that's the case because you can only have either 2 or 3 children. You couldn't possibly only have 1 child. Now, if our num data was equal to 2, we would automatically know that we are either a leaf or we have 3 children. Children at 0 would be not null. Children at 1 would be not null, and children at 2 would be not null. Lastly, if num data is equal to 3, we need to do a split. So keeping track of that information is helpful because it tells us what we need to do. If we are num data and we're doing a split, if our num data is a split and we are a leaf, is leaf and num data equals a split, we don't have to worry about any children. We just need to punch up our middle value and separate our other 2. If we're not a leaf and our num data is requiring us to do a split, num data equals 3, so a split. If we're not a leaf, there's a good chance that it means then we have children 4. We will end up with 4 children because that's really the only way that this could happen if we're not at a leaf. This scenario only occurs if this already occurred. I won't say why, because it's obvious if we know that we're always adding to the to the leaf nodes, but I would recommend that you try to prove it to yourself why we know that if we're not a leaf and we're doing a split, it has 4 children, and that this could only happen after we already did this. The only way we could end up in this position is if we split a leaf that landed us in this position down here. All right, I will leave it at that for this video. We will look at traversals and deletions in another video. So thanks for joining me, and have a great rest of your day. Bye, everyone.